Okay, last class we were discussing phi value analysis, right, and these were the last couple of slides that I went through. So, one was this where phi f was equal to 0, phi u is equal to 1, and phi f is equal to 0 means that means the phi folding is 0, because if you can see whatever difference you have in the native state, which is this, the difference in the native state, this is not reflected in the transition state, right. So, that means it does not matter what change you have in the native state, transition state does not care. That means, transition state does not have any component or does not have a component of the native state. So, whatever structure you see in the native state is possibly not being found in the transition state for you to see any effect in the transition state per se, right. So, then obviously, the other picture is the reverse of this, where so these are two extremes, right. One is whatever you have in the native structure is not found in the transition state. The other one is whatever you have in the native state is being found in the transition state. So, in that case what you will have is this, and you can see this, these are very similar, in this case the same, which means that if in the previous case phi f was 0, then in this case phi f would be 1, and obviously phi u would be 0, and this is only for a two state scenario where phi f plus phi u goes to 1. Okay. So, this is how people would interpret if they would have free energy diagrams like this, and as we were discussing last time, these are extremely important for you to figure out which amino acid affects to what extent, which amino acid is instrumental in the formation of the transition state going to the native state, which amino acid in the transition state, or rather I mean let me go back and try to rephrase this discussion. So, for example, you have a protein, say two parts A and B. Okay. Say A part is the most important part, which is the hydrophobic core, and B part is the rest of the protein, mostly the surface residues. Now, what will happen is, say suppose you have A part which is the core, you would know that if I would make any changes in the A part which is the core, then I would be having a change in the transition state, okay, and this would be reflected here. Now, how much of a change you would have would depend upon what kind of a mutation you are doing, and we talked about these mutations before. Now, go back and also think about this for the B part, where they are not really that responsible for protein stability. If you were to be making some changes, that those changes might or might not be reflected as such in the transition state, because they per se are not that important for protein stability. Now, what I am saying is not that important, it does not mean they are not important at all, they are important in their own ways, right. So, these are some of the things that people have to take care of, or people have to keep in mind when they do these mutation analysis, these phi value analysis, along with the assumptions that we discussed a little bit last time, right. You would not be undergoing a gross change in structure, there should not be a gross change in pathway and all these things, otherwise these fall out, right. Okay. So, moving forward, let us look into kinetics. So, we have talked about the effect of amino acid on the transition state through the phi f or phi u values. Now, how do we measure those effects? The direct fallout of a change in the transition state is a kinetics, right, because that is the only way you can measure your changes in transition state, no other way right now for proteins. So, what are you looking at? You are looking at something known as a chevron plot. Okay. So, let me write this here, this is called a chevron plot. Now, what are you seeing here? These black dots are experimental data, that means experimental data points. Okay. Now, what you have on the x axis is you have your concentration of denaturant, in this case it is guanine hydrochloride, you can also have urea, not a problem. Now, what it tells you is, if you look at say the higher concentrations of denaturant, say for example from 4 to 7, if the concentration of denaturant is high, what would happen to the protein? Would it be in the folded or the unfolded state? It would be in the unfolded state. So, for example, this is what you are doing, you are trying to measure kinetics, right. You are trying to measure kinetics and you have done something to the protein, you have done something very fast. Remember, you are trying to measure kinetics, that means it has to be a function of time, right. But for measuring kinetics, you have to do the change very fast, and come to that later. So, essentially what you are doing is, say for example, you are trying to look at the unfolding of a protein. So, that means you have to maintain a very high concentration of denaturant, and you have to maintain that very fast because you have to observe kinetics, right. So, what you do is, again I will come to this, but just listen to this for the time being. What you do is, you take protein, say in a syringe, protein in just buffer, no denaturant, right, and take a high concentration of buffer, or rather high concentration a buffer having high concentration of denaturant in another syringe, right. And say the final concentration of denaturant you need to have is what, maybe 5 molar, 6 molar, does not matter. Okay. So, if you are mixing it, a high concentration of denaturant and a protein in buffer which is no denaturant, when you mix it, because this is high, what will happen is the final concentration will be very high of denaturant after you mixing it, depending upon what ratio you mix it in. But the way you mix it in is making sure of the fact that the final concentration of denaturant is pretty high, say 5 to 6 molar, okay, or even more than that. Now, once you do it, what happens is you mix this, but you mix it very fast, then just like that you mix it, and there are ways of doing that. These are called rapid mixing techniques, right. The moment you have it, what will happen is the final concentration of the denaturant based on your mixing ratio and all these things, say is 6 molar. So, what you will see is that the final concentration of denaturant is 6 molar, then once you mix it, the protein starts unfolding and stops at whatever signal or whatever unfolded form you should be having at 6 molar. Did you get it or not? Again, so you have a protein in buffer, you have high concentration of denaturant, you mix these two very fast in such a manner that after mixing, the final concentration of the denaturant is 6 molar. Now, if the final concentration of the denaturant is 6 molar, then the protein has to denature, and it will stop at that conformation, unfolded conformation, which corresponds to the 6 molar guanine hydrochloride. But you are mixing it very fast. Remember, you mix it, once you mix it, the protein sees the guanine hydrochloride concentration and it starts responding to it, but it cannot respond that fast because the protein is going to evolve into the unfolded form from the folded form. That evolution in terms of time is a kinetics, and that is what your Ku is, right, because Ku is unfolding, and because you are keeping a high concentration of denaturant, again just listen to this, I will come back to this, because it is a high concentration of denaturant, you are looking at the protein being unfolded or going to the unfolded state. Is it a little more clear? Janaka still shakes his head. Janaka, keep shaking, it is good exercise, we will come back to this, right. Now, so the point was that if you are at a high concentration of denaturant, then this arm, so that means this arm is essentially your unfolding arm, isn't it? That means if you are at a high concentration of denaturant, essentially what you would be looking at is a protein unfolding, hence you would be looking at the rate constant of the protein unfolding, that is Ku, right. So, that means if you are looking at this figure, this unfolding arm, you can see all these data points are related to the Ku, and then you extend it. What you get at this point is something which you have done before in terms of delta G. What is this? This is the unfolding in absence of any denaturant, which is ln Ku H2O. Okay. Now, similarly, think about the reverse. Now, this is how people generally do it. What they do is, if you are talking about a refolding, that means you are talking about actually a protein folding or coming from the unfolded state to the folded state. So, what you do is you take the protein in a very high concentration of buffer, right. Then you mix it with buffer which is no denaturant, you mix it with a certain ratio such that the denaturant concentration becomes very low after mixing. So, you started with protein in 6 molar, then you mix it with a high concentration of with buffer no denaturant in such a ratio that the protein comes down to say 0.6 molar. Because it is 0.6 molar, then what would be the final state? Native state. And then what are you looking at? You are looking at the folding of the protein. Then which arm are you looking at? Are you looking at the unfolding arm or the folding arm? You will be looking at the folding arm, right. So, then this one is your folding arm. So, then in the graph you have two essential sites. One is the high concentration of denaturant corresponds to what? Ku. The low concentration of denaturant where the protein would essentially be folded is called what? Kf, because that is your folding arm. Now, you remember from delta G, rather from our equilibrium thermodynamics, these transitions, that does not matter where I start from, say I start from the folded state, I go to the unfolded state, in between I will be having a state, what would happen, where k equilibrium would be equal to 1. Now, if it is a 2 state scenario, k equilibrium is equal to 1 means, say you are going from the folded to the unfolded, right. So, that means you are looking at k equilibrium is equal to ku over kf, right. So, ku by kf would be equal to 1. That means, if you are very close to your midpoint of denaturation, then ku by kf would be very similar, only then you can get k equilibrium to be 1. So, if ku by kf would be very similar at your Cm, that means the midpoint of denaturation, they should be having the same value, they should, that means they should intersect at one point. So, then you can see this is the point of intersection, right. This is the point of intersection, and what does this point then correspond to? This point corresponds to Cm, right, because that is where Ku and Kf are both comparable to each other. Is it clear or not, right. So, this is now you can realize this is another way for you to check where my Cm is, right. I just drew kinetics on Ku, I just drew kinetics on the folding arm, I just drew kinetics on the unfolded arm, I extend those, right, and the place where they cross, Ku should be equal to Kf, K equivalent should be equal to 1, provided I am talking about 2 state scenario, and hence I would be getting my Cm. So, then essentially this would be my Cm. So, you can see if you look at the data points now, the black data points, they come like this from the left hand side, from the right hand side they come like this, and between they have a certain curvature. So, that curvature, that the minimum point of the curvature corresponds to what? The Cm value, because that is where k is equal to kf, right. So, now if you forget about all this and look at just the picture, does not it look like a V shape? So, this is called a chevron plot. So, that V comes from the chevron plot, this is how it is named, that is why it is called a chevron plot, it is a nice name. Okay. So, this is the essence of a chevron plot, right. So, that means by doing this you can understand if there is a difference in Ku and Kf, and hence make out which arm, that means whether the unfolded arm or the folded arm is being affected, right. Okay. Now, before I go any further, realize this, one is both of these would be having their respective slopes. So, for example, if you look at the ln Ku H2O, this is the slope of mKu. Now, remember what mKu was, we talked about this before, right, delta G is equal to delta G H2O minus m times concentration of denaturant, right, where m was related to something known as accessible surface area or surface exposure. So, the same thing you will be having here. The only difference is when you are doing delta G unfolding, you are talking about the total m, that means the difference between u and f. But in this case we are talking about two different terms. What are you talking about? One is you are talking about the difference between the transition state and the folded state, or the transition state and the unfolded state. So, that is why if it is ln Ku, then you are talking about mKu, because it is the unfolding arm, and if it is ln Kf, that is you are looking at the folding arm, that means you are going from the unfolded to the transition state and then to the folded state, then you are talking about mKf. Okay. Second point is, you look at this x axis, what is it? It is not ln K or ln Kf, what is it? It is ln K observed. Do you know what K observed this here is equal to? There has to be a relation between K and Kf, right, otherwise you will not be able to use this. Now, let us try to figure that out. Now, that is the next point of contention. Okay. So, let us look at a two state kinetics. So, that means we are essentially again looking at a free energy profile. So, that means this is F, this is U, and this is your transition state, okay, and this is G. So, if you are going from here to here, that means if you are moving over the barrier like this, that means from the U to F, what are you looking at? You are looking at a folding process. So, the corresponding rate constant would be Kf. Similarly, if you are looking at the reverse process, that is going from the folded to the unfolded state, what are you looking at? The rate constant is you are looking at Ku, right, because you are looking at the unfolding process. Simple. Now, before you knew from thermodynamics delta G unfolding, that means I am going from F to U, can be written as delta G unfolding in neat water, that means no denaturant, minus m into concentration of denaturant. Do you remember this? We had done this ages ago, right? Okay. But this was from equilibrium thermodynamics, there was no kinetics involved here. Now, how do we relate this, or is there any similarity between this one and the kinetics we are looking at? So, what people found is this. So, suppose you are looking at the unfolding, that means you are going from folded to the unfolded state. So, then what you can write is natural log of K u is equal to ln K u H2O plus m K u into concentration of denaturant. So, if this is 1, then let this be equation number 2. Okay. So, this is the linear relation. See, this is very similar to delta G u, but only in this case you are not having delta G u. What do you instead have? You have ln K u. But remember, can you convert this to a free energy form? Can you or can you not? You can, right? Remember through this transition state theory, see K is equal to nu times kappa e to the minus delta G, whichever you are looking at by RT, right. So, you can easily get that delta G, but remember in that case the delta G is always the difference. So, if you are looking at unfolding, it is the difference between the transition state and the folded state, but in this case the difference is between what? The unfolded and the folded state, it is not the transition state. So, this is why kinetics is so important here. Okay. Coming back to this again, you look at this equation very carefully. What does it say? If I am taking K u or the natural log of it, it is equal to the K u, that is the rate constant in absence of any denaturant, plus m times d, where m is m K u because you are looking at the unfolding process. Okay. So, what it means is with increase in concentration of d, what happens to ln K u? Does it increase or decrease? Keeping in mind the fact that m is always algebraically positive, it should increase, right? Okay. See, what is the essence of that? Think about this. If you are going to increase concentration of denaturant, would it be more difficult or less difficult for you to unfold? Less difficult. So, if it is less difficult for you to unfold, then wouldn't the rate constant be higher? That is what you are looking at. Very simple. Okay, nothing hidden. This is just by sheer logic, and obviously people found that it was valid experimentally, and that is what you also saw in the previous slide. I will come back to that again. Okay. So, what it means is that the more denaturant concentration I increase, which is d here, the more denaturant concentration increase d, then my unfolding rate constant would become higher, or unfolding would become faster, because I am pushing the protein more and more towards the unfolded state, and becomes easy for me to denature it, right. Now, if this is the case, then you can understand for the folded form I would be having something like this: ln Kf is equal to ln Kf H2O d. I am going to have m Kf, but I will be having a minus here. Now, tell me, is this equation logical or not? The previous equation was I go to a higher concentration of denaturant, my unfolding rate constant increases. Okay. Remember, both mku and mkf are algebraically positive, right. Now, in the second case, what does it say? What it says is, if I increase the concentration of denaturant, what happens to kf or ln kf? It decreases. Makes sense, right? Because if I am moving more and more to the unfolded state, it will become that much harder for me to come back to the native state, right. So, that is what it means. So, in other words, the lower is the concentration of denaturant, the higher or the easier it is for me to go to the folded state, and hence higher is the rate constant, which is Ku and then ln Ku. Okay. So, now if I just come back to this slide. So, if you look at the slide, can you see the slide? Yeah. Okay. So, now you can understand this a little more details. So, if you look at the right side, which is the unfolded arm, you can look at all the black points. So, the black points are fit to ln K is equal to ln Ku H2O plus m times d. On the left side you have the folded form, and that is being fit to what? Being fit to ln Kf H2O minus m times d, and that is why mku is positive in this case, there is a slope is positive, and mkf it is minus mkf, that means for the folding arc the slope is negative, because f decreases if concentration of d is increasing. Okay. This is essentially what your chevron plot is. So, nothing big. What you are just doing is you are combining two things. You are combining two forward stuff. One is the forward reaction, the other one is a backward reaction. Whichever way you are forward or backward you decide, does not matter where you start from, right. Now, this is very similar to something I think you guys have done already, and let us do it really quick. You did in kinetics. In kinetics what you did was, did you do this reversible reactions? Do you do this reversible reactions? Only one voice says yes. Okay, second. I am sure you have done it, right? Take it from me. If not from you, take it from me. So, remember, when we are talking about this folding and unfolding, we are not talking about just irreversible, it is not a one way process. Why? Because at each and every point we are maintaining what? An equilibrium between these two states, and the moment we are talking about equilibrium, in this case obviously we are trying to focus on an rather on a reversible equilibrium. Now, in that case what I can write is, say I am going from the unfolded to the folded state, right, or well, does not matter, take. So, if I do this u to f, then this one would be kf for me and this one would be ku. And please remember, again I am talking about a two state scenario. Only two states, right. So, now what I can do is, then I can write d of u over d of t would be minus k of f into u plus k of u into concentration of f, is not it? U is the unfolded form, f is the folded form, and both of these can interconvert because they are in equilibrium. Also what I have is, also what I say this is equation 4. Also what I have is concentration of u plus concentration of f is equal to concentration of u at the initial time t is equal to 0, which is u naught. So, my assumption is that when I start, concentration of f is equal to 0. So, that means at t is equal to 0, concentration of f is equal to 0 and concentration of u is equal to u naught. So, that means if concentration of u is equal to u naught, maintaining the fact that nothing is lost or gained, then u naught should be equal to concentration of u plus concentration of f at any given time, does not matter what it is. So, then I can use 5 and put it in 4. See, my rate is in terms of d over d of t, right. So, I would try to replace what I would try to replace f by u and u naught, that is essentially what I am trying to do. Okay. So, that means using 5 in 4, we can write d of u over d of t is equal to minus k f times concentration of u plus k u. Now, what I do is I replace concentration of f by concentration of u minus concentration of u naught, right. Okay. So, now if this is what I am having, I have just replaced f, I have not done nothing, I have not done much, right, I have just replaced f, that is it. Okay. Now, I split it out. So, what I have is d of u of d of t is equal to minus k f times concentration of u, okay. Then plus k u. You did not tell me I had made a mistake, but anyway I will correct the mistake here. Okay. So, what is f is equal to? So, this, tell me where is the sign mistake. So, this is minus and this is plus, right. So, then u, let me write it again, u naught. So, what I can write now is d of u over d of t is equal to concentration of u minus k u plus k of f plus k u times u naught. So, this is equation number 6. You always make sign mistakes. Okay. Equation number 6. Now, look at one thing. There is a very important thing that is cropped up. The thing that is cropped up is this guy k u plus k f. This is a parameter which tells you what? It is not one rate constant, but it is the sum of the rate constants you are looking at. Okay, it is the sum of the rate constants you are looking at. Now, what we are going to do is we are going to solve this equation. Okay. So, to solve this equation, what we do is we just integrate. So, that means what I do is I take d of u over concentration of u k u plus k of f k u u naught is equal to minus d of t, and I will integrate. What will I integrate between? I will integrate between t is equal to 0 to t is equal to t, t is equal to 0 to t is equal to t. Now, that is the integration I am going to follow, as simple. Now, on the left hand side, what are you going to have? On the left hand side, see, this is just 1 by k of u plus k of f. Okay. Then let me write this natural log concentration of u k of u plus k of f minus k u u naught, and this has to be evaluated from 0 to t. This is equal to minus t. Doable, right? A simple integration. Now, how would this simplify? Can you tell me? So, can I write this? So, 1 by k of u plus k of f natural log. See, the top one is t. So, everything remains the same. So, that means I can write k of u plus k of f times u minus k of u times u naught. Now, what comes at the bottom? Tell me quick. Remember, it is t is equal to what? 0. If t is equal to 0, what happens to u? U is equal to u 0. So, what am I left with? So, see, this is u 0 k u plus u 0 k f minus u 0 k u. So, what am I left with? I am left with k f into u naught, and this would be equal to minus t, right. So, if I do that, so what I will have quickly is natural log k u plus k f u minus k u concentration of u naught over k f u naught is equal to minus k u plus k f times t, or finally, I can write this k u plus k f to concentration of u minus k u concentration of u naught is equal to k f u naught. Then what should I write? E to the power minus k of u plus k of f times t, and this would be which equation? Equation number 7. This would be equation number 7, right. Now, guys, keep this in mind. On the chevron plot, on the y axis, what was the thing you had? You had natural log of k observed, and I told you k observed was just not k or k f. Now, do you understand what k observed is? It is k u plus k f. Okay? K observed is equal to k u plus k f. So, if this is the equation I have, I am still not reached the final form. If this is the equation I have, now tell me, when I am reaching equilibrium, when do I reach equilibrium? What is t at the time? When do I say that our system has reached equilibrium? What can I take t to be? If the initial part is 0, then what is my t at equilibrium? Can I take it to be infinity? Because what is equilibrium? Equilibrium means I have given it enough time for it to equilibrate, right. So, that means at equilibrium that is t tends to infinity, what happens to equation number 7? What happens to equation number 7 to the right side? What does it go? It goes to 0, right. So, that means the right side of equation 7 goes to 0, because e to the power minus infinity is what? 0, right. So, hence what I can write is k u plus k f concentration of u is equal to k u concentration of u naught, but this is at t tends to infinity. That means I have already reached equilibrium. Then what should the concentration of u be branded as now? It should be labeled as u equilibrium. So, quickly then I have u equilibrium is equal to k u concentration of u naught over k u plus k f, and let this be equation number 8. See, why do I need k equilibrium, or rather why do I need u equilibrium? I need u equilibrium because after I do mixing, where does my change stop? My change stops at that point beyond which there is no further change. And what is that point? The point is the equilibrium, right. And that is why the u equilibrium, or if I had gone the other way around, the f equilibrium is so important for me, because the change would stop once I have reached equilibrium, because you know at equilibrium what happens? There is no further change. Du by dt is equal to 0 or df by dt is equal to 0, there is no further change, is not it. Hence, I can use this 8 in 7, do some algebra, and finally what you will get is, I will give you the equation. So, the equation will look like this: concentration of u is equal to concentration of u equilibrium plus in brackets u naught minus u equilibrium, then this times, so this bracket times, so the last bracket times e to the power minus k u plus k f t, and let this be number 9. So, this is the final equation you have, okay, and this is the equation you are looking at. You can do one more simplification. Let me tell you what you can do is you can take u equilibrium to the left hand side, right, and then take log on both sides, or natural log on both sides. So, that means you would be having is ln u minus u equilibrium would be equal to ln u naught minus u equilibrium minus k u plus k f times t. You can easily do that, right. Okay. Now, tell me what is the significance of this equation, how do you interpret it, or how do you look at it logically. So, this is what it means if I am going to look at my kinetics, the concentration of u at any given time after I had done this should be, that means where it stops. So, that means where the change stops has to be u equilibrium under those conditions, right. Now, how did the change take place? That means how did you come from a initial condition of u naught to u equilibrium, that is what you are looking at. So, the way you came from an initial condition of u naught to u equilibrium was by doing this, by this exponential relaxation factor, which is u e to the power minus k u plus k f. So, what I can write now is, I can write then k observed is equal to k u plus k f, and this is what you are plotting on the y axis of your chevron plot. Okay. This is what you are plotting on the y axis of a chevron plot, please remember that. Is it clear or no? Is it clear to everybody? This is extremely important. See, this is why this rate constant or this method is called a relaxation method. It is called a relaxation method because you are looking at a relaxation where you have an equilibrium between two species. So, this is a method of relaxation. Relaxation means not that you are relaxing, right. What relaxation means is, that means you have started from a non-equilibrium situation and you have allowed the system to relax to what? An equilibrium situation. That is what relaxation is. And what is the rate constant of the relaxation? So, k relaxation or k observed is equal to k u plus k of f, or I can write what is the relation between k and tau. Okay. So, that means tau is equal to 1 by k observed, or 1 by tau is equal to k observed is equal to k u plus k of f, and this tau is referred to as tau relaxation. Okay. So, this is k u and this tau is referred to as tau relaxation, and that is what you do. There are ways of measuring this relaxation time constant, we will discuss those very soon, but whenever you are talking about a two state scenario, whenever you are talking about a chevron plot, you are always talking about k observed, and that is what k observed is, and that is how you derive it. Okay. So, that is what the relaxation method is. Okay. Now, how would you construct a chevron plot, right? We have seen the chevron plot. How would you construct a chevron plot? That means, how would you actually give rise to a chevron plot given any protein? Now, this is what you would do. The first thing is, if you are going to do an unfolding experiment, that means you are trying to unfold the protein and get k u. What you would do is, and those on the red dashed line, which was to the right of the curve, right. So, you see the red dashed line, this is the unfolding, okay. That is what you are trying to do. So, for unfolding experiments, what you do is, you take the folded protein in buffer and it is rapidly mixed. Remember, I told you have to mix it very rapidly, it is rapidly mixed with an excess of denaturing solution. Typically, it says 1:10, which results in a high overall concentration of denaturant, and once you have given a high overall concentration of denaturant, then you are sure that the protein is going to the unfolded state as defined by that final denaturant concentration. Okay, as defined by that final denaturant concentration. So, remember, when we were writing ln k u was equal to ln k u observed plus m k u times d, that d is what? Which denaturant concentration is that? That d is the final denaturant concentration where the protein is relaxing to, isn't it? Because that is what defines what your final equilibrium state of the protein is. That is where the relaxation should stop, or that is where the process should stop. That you have to make clear. Is it okay with you guys? So, that d, what we talked about in that equation, I forgot, was it equation 1 or 2, I guess 2 and 3, that d is your final denaturant concentration, because that is what you are defining to be the final state where I want my protein to come to. Okay. So, then if this is your unfolding experiment, how would you do your folding experiment? Or the folding experiment would be just a reverse, but before going there, what it says is, how would you monitor this? You would be monitored by some type of signal. It is an optical signal, it can be fluorescence, it can be CD, it can be just simple absorbance, something else. So, from these data, the unfolding k u can be determined, and this is plotted against the concentration of denaturant at which it occurred, right. So, this concentration of denaturant is a final denaturant concentration. So, now you can realize how do you get so many data points. Remember all those data points here? Remember all these black data points you can see, right? These black data points, how do you get these black data points? You get these black data points by doing what? By taking different final denaturant concentrations. So, different final denaturant concentrations would be giving you what? Different values, right, and then you plot those and you get your k u, because remember, with your denaturant concentration your k u is going to change too. Okay. And this I am only talking about the what? The unfolding arm. So, the folding arm you would do the same thing, right. So, in the folding arm what you would do is, for folding experiments those to the left, that means the blue dashed line, unfolded protein in high denaturing solution, you are already unfolded, but you are looking at a folding experiment, it has to be rapidly mixed with buffer, which is very low concentration denaturant, no denaturant, and then because it results in an overall low concentration of denaturant, the protein would start folding, and essentially that is what you are going to follow. Okay. So, then the same optical probes can be used, the same thing like CD, fluorescence, absorbance, whatever you use there, you can also use the same thing, and then draw the left half of the figure. And finally, you fit those, that means you join those, and what you get is your chevron plot. So, then what I can now write is, if k observed is equal to k of u plus k of f, then ln k observed is equal to ln k of u plus k of f, okay. Or I can write ln k observed would be equal to ln. Now, what is k u equal to? What is k u equal to? Can I write k u H2O, then e to the power what? M k u, what was it? This is what we are going to have, right. Remember, what did we have? ln k u was equal to what? ln k u H2O plus m k u times d. So, then if you take ln k u minus ln k u H2O, what would you have? K u over k u H2O would be m k u times concentration of d. So, then m k u or ln k u or k u would be equal to k f times e to the power m k u concentration of d. Okay, look at that. This comes from equation number 2, and for k f what it would be? So, k f would be k f H2O e to the power minus m k f concentration of d, where d is denaturant. So, what you have now is, it is very simple, that is why I said it was a fitting thing. So, you have k u from your series of experiments, unfolding experiments, you have k f from your series of folding experiments. Now, you know that your ln k observed is equal to, where k observed is equal to k u plus k f, then you just use this equation, final equation, to draw that chevron plot that fit through your data points, and that is what you have. As such, the concept wise it is very simple. Experiment wise you can understand it is tedious, right, because you have to do so many of those experiments. You have to give each time you have to give rise to different final denaturing concentrations, whether high or low, whether you are looking at the unfolding or the folding arm. But people have been doing this regularly, right. And remember, all these things are related to your 5L analysis. So, what would the, let this be equation number 10. Okay. So, then as I said, the V in the chevron plot. So, what is the V in the chevron plot? It means that the protein folds more slowly in the presence of denaturant than in pure buffer. That is understandable. This has to be, right, because remember what ln kf was? Ln kf was equal to ln kf H2O minus m kf times d, right. So, in presence of denature it would fold more slowly. Likewise, the higher the denaturing concentration, the faster the protein would fold, right. Thus, the resultant plot would be looking like a V, and hence it is called a chevron plot. This is a V shape. So, you can understand. So, this is how it comes, right. This is how it comes. You are looking at K u, looking at K f, and that is typically or essentially this tells you why you are getting a V shape. Remember, the discussion or whatever we discussed just now was based on the assumption of what? There was a very stringent assumption. What was it? Even we derived that kinetic. What was it? Two state. There was a very stringent assumption. So, possibly if you would see ever any deviations from the chevron plot, you would understand that whatever I am looking at is not strictly a two state scenario. That is also one of the ways of checking it, right. So, okay. Let me give you an example. This is for chymotrypsin inhibitor 2. Remember we talked about this with regards to that nucleation condensation mechanism and the 5-value analysis. So, see what happens. This is the wild type. Okay. So, that means wild type means you have not done any mutation. Then do you understand these are 3 different chevron plots of 3 proteins. One protein is your wild type WT, the other protein is L27A, this one L27A. What you have done is you have replaced the leucine at the 27th position by alanine, right, and the other one is your V38A. That means you replace the valine at 38th position by alanine. Now, look at what has happened. What has happened is, to the right of the figure, first of all look at the wild type. The wild type, remember from if this is a wild type, where does the denaturation midpoint come in? It comes close to about 4.2, 4.3, right. This is Cm for the wild type, is not it? If this is Cm for the wild type, so say this is what should I write? So, this is Cm for the wild type. Okay. Now, when you have gone to this mutant V38A, what has happened? What has happened to the Cm? It has decreased. Okay. That means this is the new Cm now. So, if this Cm was say 4.3 or 2 or 3, this Cm say would be what? 3.8 molar guanidine chloride. Then what has happened? As a result of the mutation, what has happened to the protein? In one word, destabilized. Okay. Now you go to L27A. Where does the Cm shift? You can see now the Cm shifts to somewhere here. So, this is would be what, 2.6 say. It is more destabilized, right, straight away you have this. So, what do you understand this? All these, both these mutations are destabilizing in nature. Now, if they are destabilizing in nature, tell me what happens. What do you mean by if they are destabilizing in nature? If they are destabilizing in nature, I do not think I have space here, but I will try to draw. If they are destabilizing in nature, now this is what is going to happen, right. So, I will use the slide, I rather use the page. If they are destabilizing in nature, say for example, this is a transition state, this is your U, this is your F. If it is destabilizing means what? Destabilizing means that the free energy difference you have between the folded and the unfolded state has decreased. Okay. So, maybe this is V28, so sorry V39, is it 38A. Okay. Now what has happened is, with L it is more destabilized. So, then it would go here L27A, right. Okay. Now, we do not know anything about the transition state yet, right, but let us look at the kinetics. Let us look at the kinetic traces. If you base your assumptions on this, okay, if we do not know anything else, see what happens as we progressively destabilize. What happens? What happens to the barrier? So, initially the barrier was this, right, the free energy barrier. You are looking at unfolding, remember Ku, that means you are going from F to U. So, this was the initial for delta G wild type. So, delta G dagger. Okay. Now, when you are going to V38A, so V38A, say if this is V38A, this would be delta G dagger V38A. So, what has happened? Already the energy difference between your transition state and steady state has decreased. Okay. So, now if you go for L27A, what will happen? It would be a further decreased. So, delta G double dagger L27A. Okay. What is Ku in terms of your transition state theory? Ku is equal to, remember, nu times kappa, that transmission coefficient, e to the minus delta G hash f by RT, because you are looking at unfolding, right. Okay. Now, you tell me, if you are destabilizing the protein, that means you are destabilizing the native state with respect to the unfolded state. Will it be easier for you to unfold or less easy for you to unfold? Think again, you are destabilizing the native state with respect to the unfolded state. That means the unfolded state stays like here, but your native state is going up, right. So, now is the energy barrier decreasing or increasing? Decreasing as you destabilize. So, if you decrease at a destabilize, what will happen to Ku? Will it increase or decrease? It will increase, right. Sure, with me on that page? Good, same page then. Now, let us go back to the slide and see what we have. If you go back to the slide, you see this portion talks about Ku, isn't it, because this is my unfolded arm. Anything beyond talks about Ku, right, that means to the right. So, at wild type, look at Ku. When you go to V38A, look at Ku. When you go to L27, look at Ku. Which has the highest Ku? L27A, and it makes sense, right, because you have destabilized so much that the energy barrier has decreased, and if the energy barrier is decreased, that means it is easier for you to unfold. It will unfold at a faster rate, and hence the rate constant has increased. And what you are plotting here is ln k, and because you are on the unfolding side, you are essentially plotting Ku, and that is why you can see these gaps coming in. Okay. Now, contrary to this, look at the folding side. Tell me, do you see that much of an effect on the folding side? The left side is a folding side, right. So, this is now this is your folding side, right. So, this is your folding side, this is your folding side Kf. Okay. Do you see that much of a difference between the kinetic between the Kf's as you saw difference between Ku's? Okay. Tell me in one word, what does it mean? See, energy between U and Ts has not changed. That means, no matter what mutations you have done out there, possibly the difference between U and Ts has not been affected that much. Okay? And as a result, the difference between the corresponding Kf's is not that huge, especially if you look at the wild type and V38A. If you look at these two curves, you see these two curves very close, is not it? Very close, but obviously L27 is a little farther off. L27 is a little farther off. So, this is how you would try to interpret a chevron plot. Okay, this is one way of looking at chevron plot. There would be other cases too. There can be a case where you do a stabilization mutation. That means, instead of the Cm going down, it can go up. So, if the Cm goes up, that means you come down, then what will happen to the rate, unfolding rate? It would decrease. So, you would see just the opposite effect. Okay. So, try, when you would look at a chevron plot, you would have to try to interpret what it means. It actually tells you a lot of things. So, this is what I have taken from Jackson, it's from first group biochemistry paper. So, then the conclusions based on this, the rates of unfolding of the mutants are faster than those for the wild type. 1. Both these mutants are destabilizing in nature as compared to the wild type. How did we realize? We realized by looking at the shift in the Cm values, and that is what we realized. Okay. Now, this is the last thing we do today, the kinetic test for intermediates. I will go through it quick. Now, in some cases what can happen is, for if you are looking at this what should I say, if you are looking at this free energy profile, right, you are going from the denatured state, which is d is a denatured state, I the intermediate, then to n. Now, intermediate has a lower energy than the denatured state, that means intermediate is more stabilized than the denatured state. Okay. And remember, the topic of this slide is how would you know whether it is an absolutely two state transition or whether it is not a two state transition, but you have intermediacy coming in, that means there are some other intermediates coming in. So, the first thing is, remember what was K observed equal to Ku plus Kf. What is K equilibrium? If you are going from U to F, what is K equilibrium? Kf by Ku, right. Now, think about this, when you are looking at this kinetics, you are getting K observed, which is Ku plus Kf. You have one equation, but you have two unknowns, you always get K observed, right. Now, then how would you figure out Ku and Kf by themselves? You take help of the equilibrium, because K equilibrium is equal to what, right. So, that means you have two equations, two unknowns, then you can easily figure out what is Ku, what is Kf. That is the beauty of having both kinetics and thermodynamics. Number 2, if you are going to make an mutation, what you would see is, okay, I have seen say a change in delta G. Now, if I ask you, or if someone asks you, do you know which arm is getting affected more, is it the folding arm or the unfolding arm? You cannot tell it from thermodynamics. Why? Because you cannot look at the transition state. The only way you look at the transition state is by what? Kinetics. So, that means you have to come back to kinetics and see which one is getting affected, Ku or Kf, and then you give the answer, right. So, these two things have far reaching consequences and are so frequently used in in biophysics of proteins. Okay. So, but anyway, so what it says is, if it is a two state scenario, my K equilibrium will always be concentration of F over concentration of U, that means the corresponding microscopic rate constants, right, and whatever Kf and Ku I get from my kinetics, they should match, because that Kf by Ku should be equal to the equivalent constant I am getting at that given concentration of denaturant. If they match, then I know exactly I am talking about a two state scenario, right. But then you see, what is the problem here? The problem here is, what would be a rate limiting step in this case? In this case, rate limiting step would not be d to n, the rate limiting step would be what? I to n, exactly. So, you would be having I to n. So, if you are ever going to have these kinetics coming in, the kinetics would not be determined by d, but the kinetics would be determined by the rate of interconversion between I and n. So, you are missing out on what? You are missing out on d, though you started with d. Okay. So, what this means is that if I have a system like this, but then one thing you are sure, right, the equilibrium between I and n would not be the same as the equilibrium between d and n. Hence, if you observe a difference between this, and if you observe a difference between your K equilibrium here and the K equilibrium you are getting from your kinetics by Kf over Ku or K over Kf, then you know for sure there is an intermediate coming in. Okay. Second thing is, the sum of the forward and the reverse m values must be equal. Okay. What does it mean? It means mku plus amkf should be equal to m, where m was defined like this before, because m is the total change between u and d. You have to be able to have that. Okay. And this is also easy in the sense that if you fit kf and ku, I mean that folding and unfolding arm, you can get mk and mkf. And last but not the least, this is something known as Chevron rollover. Remember, when we are talking about Chevron plots, they are almost linear, and we said that maybe there is an ideal case. What happens if it is not a two state scenario? See, in that case what happens? If this is your unfolding arm, this is the folding arm, when you go to the folding arm, instead of following this pattern, it actually goes like this. It shows a curvature. So, this is called Chevron rollover, and whenever you have a Chevron rollover, that means it is rolling over from its linear path, and whenever you have a Chevron rollover, that is a signature for you to say that there is an intermediate in the pathway. Okay. So, deviation from the V shaped chevron plots indicates the presence of an intermediate. Clear? So, again this is the importance of a chevron plot not only on, with respect to the kinetics, but also with respect to the test of the presence of intermediates, right. And just other points of caution before I end. Kinetic studies for the V shaped chevron plot should be made or carried out up till 0 denaturing concentration to show that there is no deviation from the kinetics in the pure aqueous solution. Okay. There is one thing we will have to do. So, that means remember that chevron rollover you had, was at a very low denaturing concentration. So, you have to go back to the denaturing load, you have to go back to as low a denaturing concentration as possible to see that they merge with each other, or you are not seeing any intermediates. And the next is, it is always advisable for those of you who would be taking these things up, kinetics and protein folding, if you are ever sticking to this field. If I have not already driven you away from that field, then it is advisable to perform refolding kinetics over a wide range of protein concentrations. Okay. Now, this we have never talked about, but remember when you have, but this we have talked about. When you unfold a protein, what happens is you expose a lot of hydrophobic patches. Now, hydrophobic patches do not like water. So, instead what they would do is they would try to look for other hydrophobic patches. So, if you have too much of a high concentration of protein, then it would be easy for hydrophobic patches to find another hydrophobic patch, and then they would come together, aggregate and give rise to aggregates. And if you are having the moment you have aggregates, then it becomes a problem, because aggregates are very hard to work with, right, and then they would show you many deviations from your chevron plot. So, you might think that this is actually intermediate for me, but it might not be an intermediate, instead it might be an aggregate. So, the best way for you to check aggregate is, see, aggregation is essentially dimerization, oligomerization, whatever. It would depend upon your concentration of protein. The higher the concentration, the higher would the rate of aggregates. So, what you do is you vary over a certain range of protein concentrations and see within what range your Ku or Kf is, rather in this case it is a refolding, which is Kf is reproducible. That is the range you take. The moment of aggregation, you will see you will be having differences coming in. So, if you are ever for people who are doing experiments, proteins are always tending to aggregate depending upon what type of protein you have. These cautions you have to maintain. Okay. So, this is typically whatever I had to talk about kinetics done, thermodynamics was done, kinetics is done now. So, next class what we would start with is we would actually start to look at instrumentation, rapid mixing methods, fluorescence, CD and all these things. That is the last part of our course. Okay.